Then what you do is, you are now, when you are doing store type of instructions, what you want to do is, you want to do, there is no destination register. Okay, so what you can do is, you want to store, take a source register, then evaluate some offset on it. So what you want to do in a store kind of instruction is, you take the source register, right, RS1, and then you are going to use, evaluate some new address, use that, and then take the contents of RS2 there. Okay, so that's what you're going to do. The B type instruction we will come back to a little later. Okay, so let us look at it. 3 operands for the store type of instruction. RS1 is the base register. RS2 is the value to be stored in memory. So whatever is in RS2 will go into the memory, right? Now the other fields are of course the opcode, right? Function 3 again is going to tell you what to perform on this opcode, right? Usually it's an addition operation only that we do. Mostly the immediate data, because you can encode negative numbers also, you just do addition and you get away with it, right? So you have, immediate 4 to 0. Remember here, there is no destination register. We are not writing into, so what is happening is 7 to 11, which was the destination register for I type, for R type, whatever it is, and load also, doesn't exist here. Okay, that's why this store type of instruction is different from the immediate kind of operation, because in the immediate operation there was always a destination register to write into. That was the common thread between what you saw in the immediate and the data. So all of them had a common destination register field, some register to indicate where to write the result into. Either you do some immediate data with the ALU and write that result into the destination register, or get the data from memory and write it into the destination register. So the store instruction is not an I type instruction because there is no destination register in this. Okay, so therefore bits 7 to 11 which were used for destination register are now available for you to encode immediate data. Therefore immediate 4 to 0, the least 5 bits of the immediate data are encoded here. Then function 3 again tells you what to do. The 2 source registers are encoded in bits 15 to 19, 20 to 24 respectively, and the higher 11 minus 5, 6, 7 bits, right, are basically encoded in bits 25 to 31. So this is sort of similar to the load type, except that the immediate data is not stored consecutively. Here the immediate data is actually split as 7 plus 5 because of this destination register not being used appropriately. Okay, so therefore you look at this, SW is to basically store a word, right? Essentially what you are doing is you are saying store word T2 comma minus 6 S3. So this is basically saying store word x7 minus 6 x19, right? So therefore in this case the RS1 is 19, okay, and RS2 is going to be 7, and the immediate data is minus 6, which is basically split across like this, right? And now the OP has to change because this is a store type of instruction, remember, right? And therefore that is 35, right? Function 3 is now going to basically do something different from this, okay. So again I leave it to you to figure out what this SH and SB operation are, right, and how that differs and how it differs from SW operation that we discussed, and how it is encoded into this instruction format. So the B type instruction, right, remember, is basically a branching instruction, okay. So what you want to do is to basically do some sort of a branch, right. So what is branching? You want to basically switch the program counter to move to some other location and execute from there. Okay, so what do you have? You have 3 operands, again RS1, RS2 and immediate. That's why this branch type is very similar to the store type. There is no destination register there, and that's why R type and B type look very similar except for the immediate encoding. Okay, so again the opcode 7 bits, that's constant. Then you have 4 to 1 out here, and then you have bit 11 stored here. Okay, the branch type is, again function 3 will tell you what to do, because what you are going to do now is you are going to do some sort of an arithmetic to figure out where the new branch address is. Okay, so let us look at that and then come back to this thing, right? So what you want to do here is you want to branch on equal. BEQ is basically you want a 13-bit immediate encodes where to branch relative to the branch instruction. Okay, so BEQ S0 T5 L1, right? What does this basically mean? It is basically going to tell you that okay, S0 is X8, T5 is X30 and L1 some relative number which is 16. Okay, so what you are going to do now is the OP is 99 obviously, right? And then the immediate data is split across these 2 fields in this very weird manner. Okay, so it's a 13-bit this thing. The first one is looks like that's always 0, and then you have bits 1 to 12 which are encoded as shown as color coded here. So the 0 is sitting on this, in this place, the blue 0 is sitting here, the red zeros are all encoded in this 6 bits as shown here, and then the immediate 4-1, right, is basically 1-0-0. Okay, and therefore the corresponding machine code is also encoded by chunking 4 bits at a time with each other, right? So this is how you basically get a 13-bit offset. So what are you trying to do here? You are basically saying, you know, you are going to compare S0 and T5, and then you are going to cause a branching operation relative to the current value of the program counter based on this immediate data. Okay, that's what you want to do here, and S0 and T5 therefore will be compared, that is X8 and X30 will be compared, right? And then you are going to go ahead and do this L1 jump. The program counter will be added with this L1 appropriately, okay, and you will jump to that particular value. Okay. Now this is another important aspect for us. It turns out that, you know, we were able to do only 12-bit immediate operations, right? If you want to bring some immediate data into a register, then you cannot do it 32 bits at a time, right? It has to be done on the lower bits. You can get 12 bits first, right? But what about the higher bits then, right? For this reason, there is an upper immediate type. So if you want to get 32 bits of data, immediate data into a register, it has to be done in 2 steps. You first get the lower 12 bits, okay, 0 to 11, and then you get the higher 20 bits, which is basically 12 to 31. Okay, so that's why you see here the jump type and again upper immediate are very similar, only the immediate encoding changes. So the U type instruction is you have an OP, okay, which is going to tell you it's an upper immediate thing, and the destination register. You are going to now load immediate data into a destination register, okay, and then you are going to do this immediate 31 to 12. So now once I tell you the register and the immediate data, you are going to move it in there, right? That's all you are going to do with it, right? Therefore all you need is the destination register 5 bits, OP is 7 bits, right? That is 7 plus 5, 12. The remaining are available for you, right, 20 bits are available for you to encode as this upper immediate data. Okay, so that is what is being done here. If you go and look at load upper immediate, LUI is basically the mnemonic that is used. S5 is basically X21, and then I have a 20 bit number. Look at this, 8CDEF. So it's 5 hexadecimal numbers, so it's a 20 bit number, and therefore you say OP equal to 55, which corresponds to the load upper immediate, then the destination register, which is 21 in this case, and then you load the immediate data into the 20 bits as shown here, right. Now the jump type, again it is very simple, similar to this instruction in its nature, and therefore it is combined like this. Okay, so you will notice that the jump and this load upper immediate are very different instructions, but they have the same structure. This basically, like I told you, depends on how many registers you are operating, what kind of operations you are doing, whether you are doing 2 source 1 destination, or just 2 source no destination, or 1 source 1 destination and immediate data. So that's how you are actually clubbing instructions and decoding, making the decoding easy for implementation in the microprocessor, right. So you have 2 operands, again RD, which is basically a destination register, and then immediate data, just like the upper immediate instruction that you have, right, and the opcode, of course, right. So again, what are you going to do here? You are basically going to say JAL, jump and link, RA comma function 1. Okay, so let us look at what you want to do here. You have basically encoded immediate data 0xA6F8. Okay, so the 20 bits are encoded like this, and they are again color coded, and they have shown you how it is being done. So JAL x1 comma this constant that you have, right. Why do you say function 1? Because typically this is used for jumping to a different function call. Okay, that's why that is called FUNC1. That this is what you see here, 0AB-C04. Okay, so is where the actual function is, but this is going to get this value will get calculated appropriately, right. So the red is available, is X20 is sitting here, the green bits are all sitting here, then the blue is sitting here, and then all the black bits are appropriately encoded as shown in this place. And X1 is basically my return address, right. RA is the return address, and that is X1 register. So the RD has value 0001, right, and it turns out that this OP is basically 111. Okay, this 111 is not binary, it is a decimal 111, and therefore you have this kind of a machine code for the jump and link as well. So just to summarize and review these, what we have discussed, there are about 6 types of instructions, right. So that are clubbed based on the instruction encoding. One is R type, which basically deals with 2 registers, 1 destination, and all of those instructions will appear here in this format. I type is basically 1 destination, 1 source and constant data, and that's going to be a 12-bit operation that you can do. Then the S type is basically the store. So the I type takes care of the load instruction, by the way. Store type is basically, again, it's RS1, RS2, there is no destination register. You are basically operating on RS1, and the contents of RS2 will be stored based on the newly evaluated address. Likewise for the B type, except for the immediate encoding format that is there. And U type is basically the upper immediate data that you want to store. So if you want to store a 32-bit constant data into a register, it has to be done in 2 steps in the RISC V architecture. First you do immediate data into the lower 12 bits, right? And then you store the higher 20 bits using the U type instruction, LUI, right? And likewise, the jump type is very similar to the U type as well. So thank you.